Hello everyone. Today I'm going to talk about my personal project called CyberEther. For those who attended last year, I also gave an introduction in CyberEther, a very different software than that is today. So I figured that would be great to give an update here. It's called a metal hardened GPU accelerated interface right now. So a brief summary of what I'm going to talk about is to just say a word about why heterogeneous computing is currently important and why will be more important in the future. And then how CyberEther came to be, a brief story, the evolution of the software, and also where the CyberEther is at this moment. And finally, a little bit on how it works. I won't get into too much detail because that would occupy like 2 hours of talks, and some future remarks. So I believe most of you know about this very popular processor. Is Apple Silicon M2 CPU, GPU, SoC. And heterogeneous computing is important because if you're just using the CPU, you're just using a tiny fraction of your silicon. Just this red box here is the CPU cores, the 8 cores, and 2 efficiency cores contains just that piece of silicon. And if you want to use the whole extent of what you're paying for, you will need to use other things like the GPU that is in the green box here, much larger than the CPU. And the other silicons is SRAM, caches, and also the NPU that Apple currently doesn't let us to use directly. So it's important to have heterogeneous computing if you want to get your value from your hardware. And also, it's important because some algorithms can't be accelerated, are very hard to be accelerated on the GPU, like closed-loop systems. So if you can share your memory between your CPU and GPU, you can use the GPU on algorithms that it's very parallelizable and get the same memory that your GPU was processing and process with the CPU much more efficiently, like closed loop and other PLL-based synchronization methods. So it's important to know what to use for what purposes. So a little bit of the story of CyberEther right now. So everything began when I started to try to learn how to use WebGL in 2021. I wrote a very brief working example of a waterfall and also a phosphor-like spectrogram that you can see in the left. And also, then I decided to take this from the browser because WebGL at the time was very limited and still is. So I started to develop the thing with like a native OS. And I said in that tweet that I would focus on trying to run this in most hardware possible. And then I started to use QFFT, that is the NVIDIA library for FFT, that is GPU accelerated. So I integrated that with the same code that was running on the browser. Now it's running it natively using CUDA. And then Dev sent me a reply and said, can we put that on an out-of-tree module for GNU Radio? And that's what I did. So there we go. We can use like CyberEther with a block on GNU Radio, and you have GPU acceleration. And also, I came back to the browser and ran the same, exactly the same code that was running natively on the browser using WebGPU GL at that time. Then last year conference came, and this was a little bit more mature. This was the interface at that time. So you can see there the line plot and also the spectrogram and the waterfall receiving a DVB signal from GNU Radio. And after the conference, my goal was to run this on the most number of devices possible. So by December, I had a working example of CyberEther running on an iPhone. So this is completely GPU accelerated, the FFT powered by VK-FFT with the metal backend and also some kernels, multiplication kernels, complex multiplication. Apple doesn't offer facilities or header files to make this easier. So I had to write my own arithmetic header that is close to qcomplex.h for CUDA, for those familiar. And also in the right there is an example of this being used in the field by detecting a microwave. I was at a facility where they put the microwaves inside cages for electromagnetic purposes to shield the emissions from the microwave, but clearly that was not working very well because I was able to detect it with my phone 10 meters away. If my phone can detect it, the telescope would do. So that's where it is working on the telephone. And also, a bunch of people last year tried to run CyberEther on their computers, and they couldn't because most of the attendants probably use Linux, so I didn't have a Linux backend at the time. So I later, a little bit early this year, I developed the Vulkan backend for CyberEther, so you can run that on Linux and also and the orb. I like the orb. It's like a constellation, but different. So Paulo Dutra on Twitter took my code, the Vulkan code, with Vulkan backend, and tried to run that on Windows. There were some patches that he had to do to make it work, but you can see there working on Windows. So it's very lots of all the major platforms, but there's more. So Vulkan also have the Raspberry Pi 4, the Videocom 4 GPU also have a Vulkan driver, and that is open source and works on Linux. So that is the CyberEther running on Raspberry Pi 4 in full HD. It also runs in 4K, but it's asking too much for that little GPU to work with. But wait, there's more. So I took my project from 2021, 2020 that translates WebUSB into libUSB, so you can talk with your device throughout the browser without even changing the libraries. So you can use librtlsdr or libaerospy to talk with your if you're SDR using the browser. No installation required. And this time, instead of using WebGL, I am using WebGPU. That is much better. The modern GPU programming paradigm for GPUs, for graphical interfaces at least. So this is completely the same code using the WebGPU backend. So we have 3 backends, Metal, Vulkan, and also WebGPU. And those 3 can support the vast majority of devices in the world. So I think that was accomplished, running this whenever I want. This is the state of art CyberEther. So you have there's I believe 30 or 60 megahertz. I can't read. Yep, it's some more there. I think Lime SDR. I'm talking receiving a LTE or 5G. I'm not sure. So, but wait, there's more. This was the where I publicized the state of the project. But right now, I have something more exciting to show. So, let's start with this. Okay, so I can't zoom out, but this is the CyberEther running with a graph interface, a nodal-based graph interface that you can access with CyberEther. So you can here, I'm not sure if you guys can see, but it's saying that it's 244 megabytes per second being processed. This is the buffer state, so no buffer being overwritten, and then this controls the frequency. But the interesting thing here is that you can interface with the nodal graphs and also have the other and have the interfacing with the nodes. So that makes things very fluid. The scaling is a little bit weird right now because scaling turns out very hard with Retina displays. If I get this, I can add a new module here by dragging and dropping a new module. So I will add another waterfall here, and then I can like GNU Radio, and then I can drop here, and this will spawn another module. Can click preview, the same thing. But the ideal thing here is that you can, so yellow is CPU, purple is metal, and other backends have different colors, and you can do this change on the fly by right-clicking and clicking metal. And that will instantly translate from CPU to metal, and you can use your whatever backend you want to use. For example, if you don't want to use the FFT on metal and you want to use the FFT on the CPU, you can click here. Everything gets reloaded. You don't even catch the difference. And the same thing is if you break a dependency from other nodes, it will immediately know that it is broken and stop the flow graph. So there's no start and stop. It's always running. If I relink this with the other module here, it will start again, and you don't even notice. And if you are, no, let me get the spectrogram view here. Drag and drop, same thing, and then you can connect. Oops. Okay, and then preview, and then you have their spectrogram there. If you want a more traditional visualization, you can create detachable windows here and there, and then create a new stack here. There's another workbench, for example, and put them whatever you want. So this and that. And then you have a very similar, familiar interface that you can use with your signals. Another example that before that, so if you hover here, you can see the pointer of the memory being used. They are all static, so you will always receive the same pointer to process. So you don't need to worry about that. If you want to do some actual DSP, you can try to run FM. I can't show the audio being demodulated here for copyright reasons, but this is the same thing, but you receive the signal here, you pass through a windowing, then FFT, then you apply your filtering, and then you get a single FM radio from that whole spectrum. And then you can demodulate with FM and then pass your auto buffer. That's the same thing that works on other platforms. Just drag and drop. For example, not sure if it will work, but the same code can run on iPad. Can you guys switch the monitor, please? No, okay, yeah, sorry. Okay, yeah, I can do this, okay. Yep. All right, so if it's an iPad app, it's running on natively on the iPad, so if I click here, it will communicate with this orange box down here that is transmitting the signal with Wi-Fi, and you can do with Apple Pencil or touching the interface. It's very fluid. And you can work on the signal like you would on desktop. So if you want to change the metal interface, just click here. It's metal. If you want to disable the module, you can. If you want to disable all the modules, you can very easily, no problem. And adding modules with this star here, the idea is to add more star in the future. So that's the same code running on iPad using GPU acceleration. If I stop sharing, so to prove that this also runs on the browser, I have here a browser. If I navigate to this address that is currently local to my machine, I have a RTL SDR connected to the USB part of my laptop. And if I click in this button here and select blog rtlsdr.com SDR and connect, and then reload the page, the browser will start communicating with the SDR using my translation layer, and then you can see the samples being fed to the browser. No installation necessary. It can run on CPU at the moment, but GPU acceleration backend for the compute modules will be added very soon. And the same thing here. All the functionality is the same. It's exactly the same code running on the browser and running on whatever else. So it's very flexible. So back here to the slides. So CyberEther itself. So it's made to be, as you guys can see, a portable and heterogeneously accelerated GUI for radio signals. It's built from ground up, using for signal processing. But right now, with the graph computing systems, you can also apply some machine learning in the future. Maybe, I don't know. And it tries to run as close as to the metal, quite literally this year, because it's running on metal, as possible using heterogeneous APIs and also very minimal dependencies. I believe that reducing the numbers of dependencies is good, because I don't want to break my stuff because others break their stuff. And local duplications, because you have, you can create a module that is kind of like a here block, so you can have a symbol of modules into a bundle and just expose the bundle to the user. So the processing, the DSP can be reused on lots of blocks without rewriting the code. And it's also easily adaptable for third-party projects. If you have an iOS app or a Windows or Linux app, you can use like the MA buff or metal surface to put in your app, just that visualization without the IM GUI thing. So it's malleable, and also the main components here is like the flow graph that is quite new. It's based on IM nodes with a little bit of modifications for it to accommodate the graphs. So you can do whatever you want there. I plan to add more examples like multi-FM demodulation with the graphs in the future. Yeah. So also LangPlot, you guys saw. The waterfalls, if you're guys familiar, and also the spectrogram. Arguably not a good name, but it works. And also the constellation that I also call as ARB. So why and how? So it's accelerated graphics at very low level. We are not running over Qt here. We are not using any other graphical interface. We are using raw metal Vulkan and web GPU to draw the things. So we can have a very, very large flexibility on where we run this and how we run this. And also the same thing applies to compute. We can use CUDA or metal or Vulkan or web GPU to do the processing and support the most number of hardware possible. And as a fallback, we have CPU compute made to run when your computer doesn't have a powerful GPU or stuff. Dependencies are not mandatory, so when you are building the project, you don't need to install all the dependencies to build. just the dependency, the minimal dependencies, like one graphical backend, one compute backend, and also some very, very little dependencies for it to build. So again, low-code duplication here, and the graphical modules are built upon a very abstraction layer that abstracts away the API. So the same code that you program a module will be applied to Metal, Vulkan, and Web GPU with this abstraction layer. It's a render. It's a very 2D optimized render, so nothing. You won't be running AAA games with this render, but it's optimized for your graphing needs. And also, instead of writing a new shader for every single backend, I implemented a transcoding pipeline that takes the GLSL and then to compile that to SPIR5 that's used by Vulkan. And that SPIR5, the same SPIR5 is transcompiled for our Metal shader language, and right now for WebGL shader language, there's another thing. Yeah. So this is called Jetstream render, and the back end can be selected in runtime. So in theory, you can change your graphical backend without even close the program. So I thought this was a design requirement more for the compute, but also applies for the graphical backend. And also the compute, if you want, as you guys can see, you can run your modules. One module that doesn't run particularly good on GPU, you can mix and match your backends, and that's completely supported. The internal graph solver will take all the dependencies between the modules, dependencies being the buffers, and identifying if that buffer goes to another domain. Because if you're doing like a Metal graph or Vulkan graph, you have a bunch of kernels being instantiated asynchronously, and you don't need to provide implicit synchronization between them. But if you are mixing and matching heterogeneous GPU acceleration APIs, you do this explicitly. For example, between Vulkan and CPU. If you have a graph that has a vector coming out from the Vulkan graph and going to a CPU graph, you need to synchronize that explicitly before executing the CPU graph. So this is all taken care of by the graph solver. Very, very low, high-level review here. It takes the raw original graph that you see at the interface. It will unwrap the bundles into a bunch of modules, and then it will take the modules, see if you have multiples, direct cyclic graphs. If you have multiple, it will run them independently without dependencies. And then each subgraph will be broken further into backend graphs. For example, in that image, you can see the first one being metal, and then you have you can instantiate 3 at the same time using the same dependency, metal, and CPU. So you can run the first 4 metals and then synchronize and run the CPU one. And that's what the graph solver will do for you. It's completely transparent to the user. And other example, more trivial, you just metal, CPU, and all the 3 metal afterwards. So yeah, it's front-end agnostic. All the visualizations are rendered in headless frames. So you can use CyberEther in a headless mode and just send the frame throughout the network if you want, or just run the CyberEther in another other program and then use DMA buff on Linux to transmit your texture and display your texture in another process. You can also integrate with Qt, Cocoa, and MTK View. That's what I do with my Apple application. I'm planning to also have an Android application next year. and it's easy to run whatever you want. So as a future, I am planning to, so this is currently all supported devices, practically almost all, and some of them can run multiple of them. For example, Mac can run Metal and Vulkan with Molten VK. iPad, the same thing, and also Linux can use either the Vulkan or Web GPU program to run CyberEther. So very also, graphical modules, you have Metal Vulkan Web GPU and CPU plus render. That is more like CPU rendering. Not great, but it's good for the debugging things, so I maintain that. Current status on compute modules, currently CPU and Metal with the compute, but I am planning to make a unified compute backend with additional supported languages, for example, CUDA Vulkan with a K, not a C, and Vulkan Web GPU. And that will try to break even further the graph, so you can take like two multiplications and merge those kernels into a single multiplication, single kernel with two multiplications, or even broadcast the arrays between like multiplication, and you have a filter for each module, and then you can broadcast the filter with the input and get a more efficient way to run those. And for the near future here, make CyberEther available either on iPad and iOS applications. I already have a working app, as you guys can see. I am planning to release that with TestFlight very soon, and also release on the browser like cyber.luigi.ltd, my website. You guys can, in the future, will be able to use your RTL SDR and build your own grabs, and also increase the reliability of DSP reliability, fidelity. There's no demo. Yeah. So thank you for listening to me. This is not the end of CyberEther. I'm planning to adding more features next year. I hope to see you all to hear that next year. If you have any questions, thank you.
Yeah. I had one question. When is this going to work with GNU Radio? Or I don't know. Is it going to replace it, or is it going to work with it? Because it was awesome. Oh, I was just kidding. I'm sorry. Derek gave me the meanest looking face when I said replace. When is it going to work with GNU Radio, do you think?
The out of 3 module is there. I didn't update it in a while because I was trying to make this work for the conference, but I will.
Or someone else could.
Oh yeah, GREther. Go there.
Time for one more question. Anybody? All right, with that, let's thank our speaker.
Thank you.